Have you ever stood at the base of a massive skyscraper, looked all the way up, and just wondered, how on earth is that thing still standing? It seems to defy gravity, swaying gently in the wind, a giant metal and glass needle pointing to the sky. Why don't they just fall over? It's a question that combines incredible engineering, a deep understanding of physics, and a little bit of architectural magic. Today, we're going to unravel the secrets that keep these colossal structures firmly planted on the ground. First, let's talk about the foundation. You can't build a giant without giving it a solid pair of boots, and for a skyscraper, those boots are buried deep within the earth. The foundation is arguably the most critical part of the entire structure. It's not just a simple concrete slab. Engineers have to analyze the ground beneath the building site with extreme precision. Is it solid bedrock? Is it softer soil or clay? The answer determines the type of foundation needed. For sites with strong bedrock near the surface, like Manhattan, engineers can anchor the building directly onto the rock. This provides an incredibly stable base. But what if the bedrock is hundreds of feet down, or the ground is soft and unstable? That's where deep foundations come in. This involves driving long, sturdy columns called piles deep into the ground until they hit bedrock or a sufficiently stable layer of soil. These piles, made of steel or reinforced concrete, act like stilts, transferring the immense weight of the skyscraper from the weak surface soil down to the strong, stable earth below. Think of it like a table. The building is the tabletop, and the piles are the legs, ensuring everything stays level and secure. Another method is to create a massive, thick concrete mat, sometimes called a raft foundation, that spreads the building's weight over a large area. This is like snowshoeing. By distributing your weight, you avoid sinking into the snow. For some of the world's tallest buildings, they use a combination of both piles and a mat foundation for maximum stability. The foundation for the Burj Khalifa in Dubai, the world's tallest building, used 192 concrete piles, each buried over 164 feet deep. That's a lot of concrete just to get started. So the building is anchored to the ground. But what about the structure itself? How is it designed to handle its own incredible weight? This is where the skyscraper skeleton comes into play. Early skyscrapers used a heavy, rigid steel frame, like a massive grid. Each beam and column was bolted or riveted together to form a strong but very heavy box. Modern skyscrapers, however, often use a more efficient design called a tube system. Imagine the building's exterior as a hollow, rigid tube. The outer walls are designed with closely spaced columns and beams, making them the primary load-bearing structure. This design is incredibly strong and stiff, resisting lateral forces like wind far more effectively than a simple internal frame. There are variations of this, like the tube-in-tube system, where an inner core tube, usually housing elevators and utilities, works together with the outer tube to provide even more rigidity. The Willis Tower in Chicago, formerly the Sears Tower, is a famous example of a bundled tube design, where 9 individual tubes are bundled together, creating a super strong and stable structure that could be built to such a great height. This brings us to the biggest challenge a skyscraper faces every single day: the wind. You might think gravity is the main enemy, but for tall, slender buildings, wind is the true test of their strength. When wind hits a building, it creates pressure on one side and a suction effect on the other. This pushes the building sideways. Even worse, as the wind flows around the building, it can create swirling vortices, a phenomenon called vortex shedding. If these vortices form at a frequency that matches the building's natural resonant frequency, they can cause the building to start swaying uncontrollably. It's the same principle as pushing someone on a swing. If you time your pushes just right, they go higher and higher. For a building, this could be catastrophic. So how do engineers combat the wind? The first line of defense is the shape of the building itself. Sharp, square corners are terrible for wind. They create a lot of turbulence and drag. That's why you see many modern skyscrapers with curved edges, tapered profiles, or even strategically placed openings. The Shanghai Tower, for example, has a unique twisting design that reduces wind loads by an incredible 24%. This not only makes the building safer, but also saves millions of dollars in structural steel. But even with an aerodynamic shape, a skyscraper is going to sway. It has to. If it were completely rigid, the stress from the wind would eventually cause it to crack and fail. A little bit of flexibility is key. The goal isn't to stop the swaying altogether, but to control it and keep it within safe, unnoticeable limits. That's where some truly ingenious technology comes in: the tuned mass damper. A tuned mass damper is essentially a giant, heavy pendulum or block, often weighing hundreds of tons, located near the top of the skyscraper. It's connected to the building with springs and shock absorbers. When the wind pushes the building in one direction, the damper, due to its inertia, swings in the opposite direction. It's tuned to the building's natural frequency, so it effectively counteracts the swaying motion, canceling out the energy from the wind. It's like having a built-in counterbalance that calms the building down. One of the most famous examples is in the Taipei 101 Tower in Taiwan. It has a massive 728-ton golden steel pendulum suspended between the 87th and 92nd floors. It's not hidden away either. It's a tourist attraction. You can literally watch it in action, gently swaying to counteract the forces of strong winds and even tremors from earthquakes. It's a beautiful and powerful demonstration of physics at work. Some buildings use a different approach called a sloshing damper, which is basically a huge tank of water. As the building sways, the water sloshes back and forth, dissipating the energy in a similar way to a solid mass damper. And we can't forget about earthquakes. For skyscrapers built in seismically active zones like Tokyo or San Francisco, designing for earthquakes is paramount. The principles are similar to dealing with wind. The building needs to be able to flex and absorb energy. In addition to strong, ductile frames that can bend without breaking, many earthquake-resistant buildings sit on what are called base isolators. These are like shock absorbers for the entire building. They are pads made of layers of rubber and steel that sit between the building's foundation and the main structure. When the ground shakes during an earthquake, the isolators flex and deform, allowing the ground to move underneath the building while the structure itself remains relatively still. It essentially decouples the building from the violent motions of the earth. So the next time you look up at a towering skyscraper, you'll know it's not just standing there by chance. It's standing because of a deep foundation gripping the earth, a super strong and efficient structural skeleton, an aerodynamic shape that slices through the wind, and a hidden heavyweight champion, the tuned mass damper, fighting a constant battle against the elements. It's a symphony of engineering, a testament to human ingenuity that allows us to build these incredible structures that touch the clouds and, most importantly, don't fall over. Thanks for watching. If you found this fascinating, don't forget to hit that like button and subscribe for more deep dives into the world of engineering and technology. See you in the next video.